Hi everyone, I'm Botao. Today I'm very glad to talk about our recent work about the event camera called Microsaccade-inspired event camera for robotics. As most of you may be very familiar with the event camera, but I think the, most of you may feel unfamiliar about the microsecond. So uh, I have a brief video to introduce microsecond.
Human beings actively perceive the world through eye movements. Regular eye movement alternates between saccades and visual fixations. Even during visual fixations, our eyes are never completely still, as there exist microsaccades. Microsaccades are a kind of fixational eye movement. It continuously stimulates the visual neuron by constantly jittering the eyeball. Microsaccades are believed to enhance the vision of fine spatial detail and prevent the retina image from fading. The following demonstration interactively illustrates the effect of microsaccades. Viewers may watch this movie in full screen mode. Demonstration interactively illustrates the effect of microsaccades. Viewers may watch this movie in full screen mode, stay close to the screen, and fix the gaze on the red spot. You can pause the video here to observe.
Okay, could everyone just set the screen into the full screen mode and stay like 40 centimeters or 30 centimeters away from the screen and put your gaze at the red spot. For a little while, you may see the bluish area and just fade away.
After seconds of fixation, you may observe the image fade, like this. This is due to the suppression of microsaccades.
Yeah,
For
just like
comparison, viewers can then fix the gaze on the moving red spot. You may observe the elimination of perceptual fading because of microsaccades.
So, even if we fix our gaze at the certain static object, our eyeball is not completely static. If it's completely static, the static background would fade away. So let's go back to the event camera. I think I think most people are quite familiar with this with sensor. It has many advantages, like since it only recorded the brightness change by pixel, so it has very its data representation is sparse, and it doesn't suffer from the motion blur, and it have very low latency, like microseconds seconds. And also, however,
Anamorphic vision sensors, or event cameras, have made visual perception of extremely low reaction time in microseconds possible, opening the doors for high dynamic applications in robotics. Anamorphic vision sensors.
however, along with its huge advantages, it comes along with some disadvantages. One of them is it loses texture that is parallel to its moving direction. As you can see in the video, when the camera moves horizontally, the horizontal edge becomes invisible. However, when it moves vertically, the vertical edges becomes invisible.
Regardless of the chosen data representation, parallel edges aligned with image motion become invisible, and textures fade as motion decreases. This is a problem intrinsic to the sensor and therefore challenging to solve algorithmically.
Even if we reconstruct the event data into the grayscale images, it also suffers from the we call perceptual fading. So can we do better? Can we utilize the advantage of event cameras with regard to its like low latency and high HDR, and also doesn't suffer from the motion blur, while we also keep the texture stable, just like regular RGB cameras. And this is the focus of our work.
In this work, we proposed a hardware-software co-design to introduce Microsaccade into robot vision systems. We designed an event-based perception system capable of simultaneously maintaining low reaction time and stable texture. Emulating the microsaccade mechanism, in this design, a rotating wedge prism is mounted in front of the aperture of an event camera to omnidirectionally stimulate events. Moreover, the geometrical optics of the rotating wedge prism allows for algorithmic compensation of the additional rotational motion, resulting in stable texture appearance and high informational output independent of external motion. Details about the microsaccade's general.
So the basic idea is, from the hardware perspective, we introduced an actuator drives a wedge prism to provide constant motion to the image plane, so that even the static background can continuously trigger events on the image frame, so that the static background can be observed by the event camera. And also, since the motion is observable by the actuator encoder, it can be compensated so that the output data format of our system is aligned with the traditional event camera, so that it is compatible with previous event-based like vision processing algorithms. Next, I will briefly talk about the generation process and the compensation process of our artificial microsaccade mechanism.
This movie introduces our mechanism for generating and compensating artificial microsaccades. To generate events on all edges, we utilize the working principle of the wedge prism deflector. When the prism rotates, it actively adjusts the direction of the incoming light. Here we illustrate our hardware design. It features an actuator driving a rotating wedge prism and recording its circular path. This rotation induces continuous changing motion in the camera, capturing all scene boundary information. After that, because the introduced motion is observable by the actuator encoder, we can compensate for events triggered by the same incoming light ray direction to the same pixel. Finally, we can get sharp and stable edges. The compensation algorithm makes our system a plug-in and use solution with existing event-based perception algorithms.
So briefly, the generation is by the hardware and the compensation is by the software.
This move.
And we apply our system to various vision tasks. For low vision tasks, we choose feature tracking and motion segmentation to validate the performance of the proposed system. So we conduct our experiments in these 4 scenarios. The first one is structured environment. The second one is unstructured complex environment. And the third one is with challenging illumination, like with very high dynamic range. And the fourth one is motion segmentation. It's a highly dynamics environment. For the first 3 environments, we detected the corner feature and tracked the corner feature. But for the fourth one, we detected the motion feature and segmented the motion. So for the structured environment, as we can see, the grayscale camera and our system both performs well, but the standard event camera, because it cannot see the features along with its motion moving direction, its corner detection and tracking performance becomes unstable. And in unstructured environment, our system is not as good as the grayscale camera, but also but still outperforms the standard event camera. For the HDR highly dynamic range environment, the grayscale camera just cannot see anything. But our system, along with the standard event camera, can still capture the corners and track it. And our system have a better tracking performance than the standard event camera. So for the motion segmentation, we can see our system still preserves the feature of the event camera about the low response time and robust to the moving scenarios. But for the grayscale camera, it just cannot detect the fast moving object. And also, we also tested our system in high-level vision tasks. We choose the human detection and pose estimation to validate our system. As we can see, when we try to reconstruct high frame rate videos from the events for the standard event camera, some parts of the human is static and some parts is moving. For the moving parts, it can reconstruct great, but for the static parts, it will suffer from we call perceptual fading. However, our system is stable even under very high frame rate. And for the post estimation, we also can achieve accurate and robust performance. As you can see, our system performs better than the standard event camera, even for the 3000 frame per second. And thank you. That's all my presentation. Is there any questions?
Yeah, thank you. So you can post questions in the chat, or you can raise your hand and ask directly. We also should say that this paper is now accepted and will soon appear in Science Robotics, and the blueprints will also be made available, so people can do the same thing, make the same thing along with the code, of course.
Yes, we open sourced all our hardware and software. I'll attach the link in the chat. Okay, is there any questions?
There is one question in the chat, Botao. I'll ask it. Can you add the reason why the corner tracker is failing at times, even though your images look very consistent? From Paul Kirkland.
Add to the reason. Which camera are you talking about? Is that our camera or the
standard camera? Why the standard BBS fails on corner tracking?
Well, not even just the standard one. So, in your method that you show that it works. The images look amazing, but your corner tracker's flickering. Why is it flickering?
Oh, you mean the
images look so stable. I don't understand why the corner tracking fails. Like the images look so consistent, and on any of them, you see it flickering on and off, but there doesn't seem to be a valid reason as to why. Like the corner was there the whole time and didn't move. The corner remained in the visual field. Like why did it? When you play the video, you see it jumping around or missing corners compared to like the RGB camera. So what's missing?
I think the first reason is it introduced like periodical periodical motion. However, the algorithm we adopted is not adapted to this kind of data format. So sometimes it becomes unstable. You mean just like this? And another reason is it's not just the detection, it's also about the tracking. Every red dot on this image marked a feature that is stably tracked for over 112 milliseconds. So sometimes it's like 4 or 5 frames. If one of these frames it failed to extract the same feature, then we don't count it as a stable tracking. Yeah, I think that's a reason. Does that make sense to you?
Yeah, that was So you've just got a really difficult task you're trying to do, or you've set a really high threshold for the tracker to exist.
Yeah. Yes.
I was just wondering if it was like an event-based method for corner tracking you used, or if it was just a traditional method that you've just adapted to this task.
Yeah, it is traditional method called EFAST, event-based fast corner detection. And for the tracking, I just write nearest neighbor matching from scratch. So I think also maybe my nearest neighbor matching is also not that good. Yeah. Any other questions?
No?
I also attach the.
Oh, there's another question, Levi.
Yes. Guillermo asks, the prism in the front of the lens reduces the field of view. How much does it reduce the field of view?
I think it's for a 0.5 degree prism, it reduces around 5 pixels, maybe, and for the 1 degree, it decreases about 10 pixels.
That's the amount of deflection, right?
Yes, that's the amount of deflection.
Right.
All right, but the field of view that you finally have in the lens, I mean, could you use this? It looks like it's like for applications with telephoto, right? But would you use this for visual odometry?
Yeah, I tried. Levi, could you please mute yourself? Okay, thank you. Yes, we do try this experiment. However, as you can see, in the visual odometry, we tried in the outdoor scenarios. It's not, I think that's because just the regular things, it's not as good as the traditional grayscale camera, because the grayscale camera can always track some features. I think it will be better in some extreme cases, like very high dynamic range scenarios or some other scenarios. Yeah.
So the camera is, if I may follow, but I'm not right, sorry. Don't wait for me to write it, to say it. It seems like the camera is kind of like converting, it's producing like events that it's like a edge detector, like a spatial edge detector, no longer like a temporal edge detector, but you compensate it in the end. It's like an asynchronous Sobel detector, right? Could you comment on that?
Oh, yes, I think so. Yes. So after the compensation, our accumulated event image basically looks like the edge image extracted by the grayscale camera. Yeah. But it preserves the advantage of the event camera, like the high temporal resolution and high dynamic range. Yes.
Have you tried with higher resolution event cameras that produce many events, and now with the prism in front, produce always events? And see
yeah, we tried this. You mean high resolution event cameras? Like we tried the Innovation Explorer, like its resolution is 640 by 480. Yeah. But we haven't tested on the up to like latest event camera that can achieve higher resolution.
The question was if you found bandwidth problems or not, like drop-in events.
Oh yeah, we do have a bandwidth and analysis in our paper. So for the wedge, so that depends on your. Yes, the short answer is yes. Sometimes the event amount will just exceed its bandwidth, but it rarely happens because in most scenarios we need the compensation accuracy instead of the amount of events. So we can use very small wedge prism. So it doesn't trigger much events, but it also preserves the edges and achieve very high accuracy compensation. But if our task needs a huge amount of information, we choose the larger wedge prism, so it triggers much more events, but have a relatively low accuracy on compensation. Sometimes if we choose a really big, like tilted the wedge prism like 2 degree, then the problem can happen. Yeah.
Very nice work.
Thank you.
So thank you, Botao.